Now that you have read the specification for Programming Assignment 1, let's go into that specification in some detail and give you any information that you might need to be able to solve the problem. First and foremost, you need to be sure that you read and understand the assignment. Errors that people made in Programming Assignment 0 mostly came down to not reading the assignment, not doing what the assignment said to do. So for Programming Assignment 1, if it says, if this error case happens, you have to generate an error message in this particular format, make sure you generate the error message in that particular format. If it says it has to be in all capitals, make it all capitals. If it says it has to have a space between things, put a space between things. Otherwise, things won't match. The other thing you need to do with this assignment, as with all programming assignments, decide on the information that you're going to need and the stuff that you're going to need to keep track of in order to do your assignment. It is said in the software business that data structures programs. The data that you need to create and maintain and manage oftentimes determines the layout of your program. So you have to read through a file and count how many characters there are. So you need a variable to keep track of a counter of those characters. You need a loop to loop through and read the characters. You update the counter as you go through the loop. And then when the loop's over, you print the answer out. Data structures program. So think about the data that you're going to need to keep track of. Now there might be some things that you need to do, some techniques that you need to apply, and you might not know how to do those things. So one of the things I want to do in this deck and some of the others is to go over what some of those piece parts are. Are there particular algorithms that you're going to need to use? What might they be? How should you save the data? What's the best and most convenient way to save the data? So I hope to review all of that in this deck. First thing I want to talk about is I/O. The assignment says that you have to either read from standard input or read from a file. Reading from a file is something we haven't talked very much about, but it's actually pretty straightforward. We already know how to read from a stream, and it turns out that it's pretty easy to create a stream representing an open file. If you want to do that and you open up a file, once you've opened up that file, all of the things that you know how to do with streams like cin work on the file stream. All you have to do is pound include fstream to get access to file streams. And once you do that, you can open up files and then read them like they're streams, because with this data structure they are. So if you take a look at this code fragment here, we've declared a variable called ifstream, whose type is ifstream, input file stream. The name is infile. So that's a stream, but it's a particular kind of stream that's associated with a file that you're going to take input from. In order to take input from a file, you first have to open it. This is a concept you're familiar with from other languages. So you say infile.open and you give it the name of a file. Now you notice that up at the top of the code, I checked to make sure that argc was the right size, so that I knew for sure that there was an argv sub 1. If I try and access argv sub 1 and there isn't an argv sub 1, I'm accessing outside the argv array, bad things happen. Okay, so I want to open up the file. And if I open up the file with the open method, maybe it succeeds, maybe it fails, I need to check. If a file is open, its isOpen method will return true. So if I try to open up a file, and at the end of executing that open, it isn't open, that is to say, if isOpen returns false, I couldn't open the file for some reason, so I have to print out an error message. Note in Programming Assignment 1, there's a thing in the specification that says, if you can't open the file, print out this message. This is how you say, I can't open the file. Now, once I've got this file open, it's a stream like every other stream, and I can use it like any other stream. So you see, near the bottom there, I say infile greater than word. From the standpoint of the program, that's almost exactly the same as if I said cin, read from the stream, a string, and put the string that you read into Word. And then differences between streams like cin and cout and file streams is it's not a bad idea to close the file at the end. That's what the infile.close method does. It turns out that the system will clean up after you, so if you forget to close, it'll usually clean it up anyway, but it's a good idea to close it. Okay. But the assignment doesn't just say to read from a file. It says, well, maybe I want to read from a file. Maybe I want to read from standard in. How do I do that? Well, here's how I do that. Both standard in and files are streams, right? We said that, and you could see that stream methods work on them, so they must be streams. They're both actually of type iStream. The stream that you read from cin, the stream that you read from a file, they're both iStreams. The code for dealing with an iStream that is cin and dealing with an iStream that is a file can be mostly the same. It's just a matter of how you set the variables up. So I show you this here using something called pointers. We'll get to that in detail in future lectures, but for the moment, what are we talking about here? iStream start in equals ampersand cin. What does that say? Well, in is a variable. It's a variable of type iStream star, which means pointer to iStream. Cin, well, we know what that is. Cin is is the standard input stream. So what is ampersand cin? It's address of cin. So what I'm saying in that line is in is a pointer to iStream. Make the pointer point to cin by initializing it with the address of cin. Great. The next two lines show a slightly different scenario. In the next two lines, I've created an if stream called file. Yeah, I did something with it. I opened it, let's say. And then instead of saying in equals address of cin, I say in equals address of file. So I'm saying make the in variable, which is a pointer to an iStream, make it point at file by initializing it to the address of file. So either in points to cin or in points to the file. Once I do that, I can just use that pointer to do whatever I might want to do with that stream. Let's say I want to get a character. Streams have get methods. So you see that in dash greater than symbol. Dash greater than looks like an arrow, right? Take in, which is a pointer to a stream, follow the pointer, that's why that arrow symbol is there, and call its get method. Call the get methods that's associated with the stream that in points to. So what does get method do? It goes to that stream, reads a character, and sticks it into ch. Have I read the stream that's cin? Or have I read the stream that's the file? I don't know. I don't care. It doesn't matter. I've initialized the pointer to point at the stream I want to read. I read the stream I want to read. All is right with the world. Now, there are several ways of reading input, right? And you know this if you're a Python programmer, and you've seen this in other languages as well. Maybe I just want to read a character at a time. Maybe I want to read a word at a time. Maybe I want to read a line at a time. And all of these things are possible in C++ with streams. If you decide that you want to read a character at a time, you can use the get method. Get a character, right? That's great. You just keep calling get until it fails. Now, here's the thing. If you're reading a character at a time and you're trying to assemble things into either a collection of characters which are not white space, also known as a word, or a collection of characters which are white space, the delimiters between words, you sort of have to write your program to keep track of what you're doing. So at any given point, your program is either in the middle of reading a word or not in the middle of reading a word. And how it behaves depends upon the character. So if I'm in the middle of reading a word and I see a letter that is, or a character that is not white space? Well, I'm in the middle of reading a word, and I've seen a character that belongs in a word, so keep that character. Add that character to the end of the string. If, however, I'm in the middle of reading a word and I see some white space, well, that means that that white space doesn't belong in the word, and I must be done with the word. So deal with the word that I'm done with, process the word, and then change your mode from I'm in the middle of recognizing a word to I'm not in the middle of recognizing a word. And the flip side of that works as well. I'm not in the middle of recognizing a word. I see white space. I just accumulate all the white space. Great. If, when I'm finally done, how do I know that I'm finally done? I've accumulated a bunch of white space, and then I see a letter that is not white space. Well, that means that must be the beginning of the next word. So I'm finished with the white space, deal with it, process it, and then switch back to I'm in the middle of reading a word mode. And that all works great. Sounds a little complicated, but it's actually pretty straightforward to just switch back and forth from state to state. Now, you could instead decide that you want to read a word at a time, right? And that works. And it turns out that white space delimiters are a concept that is known to streams. And you can use the greater than operator, the operator that's been overloaded to handle input from a stream. That handles white space delimiting. It throws away the white space at the beginning, and it stops at white space at the end of the word. Now, that's great, except that in this assignment, we need to keep track of the white space. So a solution that throws it away might be a problem for us. But okay, we can figure something like that out. The other thing, of course, you can do is read input a line at a time. Hey, you want to read input a line at a time, that's also fine. You simply use a getLine method of some kind, reads an entire line in. Now, getLine also works great, but there's a couple things you have to know about it. One thing is that getLine reads in a line, it knows that it's done because it sees a new line character, and it throws it away. So calling getLine and successfully reading a line means that you read a line in, but you're never going to see the new line character. So you can't count lines by counting new line characters you see. You have to count lines by counting calls to getLine. And even if you do that, the other thing you have to do is, okay, now I've read a line into an entire string. There's words in that line. I've got to bust up that line into words. So, I can make a single call to read a line in, but then I have to break things up into words. I have extra work I have to do. So while you could make any one of these things work, my suggestion to you is that you do programming assignment 1 by reading things in a character at a time. You don't have to worry about the extra overhead around how to handle the white spaces or how to break up the line into words. As part of doing this assignment, you also have to classify input. Is there an easy way to check if a particular character is a letter, a digit, an uppercase, a lowercase? Yes, it is. There is a way to do it, and the way to do it is to use something called CC-type, which is one of the other PowerPoint decks that's available. It's something that's available in the standard library. You can just use it. It's a lot easier to do it than, well, it's the easiest way to do it, let's say that. I also have to save words, right? I need to keep track of all the words that are of length equal to longest word. So I need some mechanism to save a collection of words. Can I do that? Yes. There are various collection types available, which I also talk about. There are vectors, there are maps. You can use either one of those. And we'll talk more about those both in this presentation and in a later one. Okay. When you structure the program, when you write the code, you should, it's good practice to do all of the argument checking at once at the start of the program. Do it one time, do it all at once, do it at the beginning, right? Now, it turns out that if you think about the different possible arguments, there are 5 different possible flags. Each one of those flags has 2 different possible values, right? So there are 2 to the 5th power possible combinations of argument settings, which, if you had to handle that by writing 32 different programs, that'd be an ugly mess. But in reality, this is just one program, which has some minor differences here and there based upon what flags are set. So the best way to structure a program here is to say, at the beginning of the program, look at flags, remember what flags were set, and set a Boolean variable to remember each flag that was set. And then simply change the behavior of the program based upon the value of that Boolean. So you don't write 2 separate programs, one that works in quiet mode and one that doesn't. You write one program, and at a place where you're getting ready to generate output, you say, if quiet is equal to false, actually generate the output. And if quiet is true, the run of the program will just skip that code. So the command line flags specified in your assignment change the behavior of the program. You should, up at the top of your program, do all of the argument checking, handle the cases of invalid arguments, handle the cases of invalid combinations of arguments, all that jazz. Then run through and keep counts. You're keeping several kinds of counts. You're finding the longest of several kinds of words. And you should note that what you think the longest word is something you calculate while you're running the program. And your idea of what the longest word is and what the length of the longest word is going to change during the course of the run of the program. Finding the longest word in a bunch of words is similar to finding the largest integer in a bunch of integers. It's the same kind of algorithm. And we'll talk about that in a sec. You're going to have to keep track of some information. You're going to need variables to keep track of that information. You'll need variables for flags. You'll need variables for the various counters that you're keeping. You'll need a variable for your current idea of what the length of these various longest words are, and you'll need some way of keeping track of those longest words. So you need a container of some kind. And there's a bunch of different ways to do this. The 2 easiest ways to do it are to use the vector container and the map container, and there's material about both of those containers. A vector is a thing that handles some memory management for you. It kind of looks like an array. It's easy to add things to. It's easy to look through everything in that vector. It's easy to throw away everything in the vector and empty it out. There's a single method for that. That's great. The only disadvantage in this particular application is that it's kind of expensive to see if a word is already in a vector. If you want to keep track of all the longest words and you want the list to be unique, I found a word of this length. This length is equal to the length of the longest word. Do I already have this word in my container? What I have to do is search the container, see if it's there. And if I search the container and find it there, I don't add it again. So that search the container and see if it's there is an order n operation. So it's a little expensive. Maps are another kind of container, a little bit different. They are also easy to add things, iterate through, clear things. All that works great. It is slightly more expensive to add things to a map because because of the way maps are structured. The internal data structure has to be rearranged a little bit, and it might take you a little bit more time than just adding something to the end of what looks like an array. However, all of the necessary management of duplicate words is done for you, right? You just say, stick this in the map. And if it's already there, well, it's already there. And if it's not already there, it just adds it. Another advantage to maps is when you look through the map, the information comes out of the map in order sorted by key. So if you want an efficient way of keeping track of a bunch of things and have those things be sort of automatically available to you in sorted order, map is a pretty good way of doing it. And for those of you who are Java programmers, a vector is kind of like an array list, and a map is kind of like a hash map. So these might be familiar things to you. Now, as for algorithms, finding the longest word is similar to the algorithm for finding the longest integer in the list, right? How do you find the longest integer in the list? You start off assuming that the largest integer in the list is the biggest negative number of all. And then you look at each integer one at a time and you say, is this particular integer I'm looking at bigger than what I currently think is the largest integer in the list? If so, it's the new largest integer in the list. And when I'm done going through the list, I know what the largest integer is. Doing this with strings is the same. Keep track of some number representing the length of the longest word. And keep it in some integer variable, initialize that to 0. Right? Every time you find a word, figure out how long it is. If that length of that word is longer than the current longest word, well, this is the new longest word, and this is the new length of the longest word. Throw away everything that's in your container with the previous length, and now you got a new length, and everything works great. And you just keep doing that. When you get to the end, you discover that you have an integer that contains the longest, the length of the longest word, and you have a container which contains all of the longest words. So you're in great shape. It's very easy to prove that this is correct, but I'm not going to require that proof. And remember, you also have to remember the longest words. And so when you change your idea of what the length of the longest word is, all those other words that you'd previously collected are wrong, right? They're no longer long enough. So you throw them out. You just clear the container out and populate it with the new word that you just discovered. And if you execute that algorithm, you should be able to collect all the information that you need to generate the output that the various options require for this programming assignment.